This is a prime number. It has 687 digits, but it doesn't even come close to the biggest prime number we know. As of 2024, the biggest prime number we know has almost 25 million digits. It was discovered in 2018, and despite its size, it can be easily written as 2 to the power of 82,589,933 minus 1. Humans have been looking for prime numbers for a very long time. We still haven't found the formula for generating prime numbers. However, we have developed methods to discover increasingly larger primes. You might wonder how we know that we haven't yet found all primes and there are always more prime numbers to look for. Around 300 BCE, Euclid showed that there are infinitely many primes with this simple proof. This proof uses the fact that every composite number can be uniquely represented as a product of prime numbers. For example, 260 can be written as 2 times 2 times 5 times 13. Let's assume that we have found all prime numbers and contained them in the list P. Now we can multiply all numbers from this list and add 1 to the result to get a number which we will call Q. This number is either prime or composite. If it's prime, our assumption that we have found all prime numbers was wrong. If it's composite, then we can write it as a product of prime numbers. Q is not divisible by any of the numbers in the list P, because after dividing by any of them, we get a remainder of 1. This means there must be a number outside the list P that is prime, so our initial assumption was wrong, and it shows that there are always more prime numbers to discover. Checking if a number is prime seems straightforward. We can just see if any smaller number divides it. However, this method is very slow. For example, to check if 1,000,001 is prime, we need to test it against 999,999 other numbers. But there's a more efficient way to do this using a simple fact about divisors. Divisors always come in pairs. Knowing this, we can stop searching for divisors of a number after we cross the square root of that number. We can also use the fact that any composite number can be written as a product of prime numbers. It means that we only have to consider prime numbers when we are looking for divisors, specifically those up to the square root of the number. However, to apply this method, we must already have a list of which numbers are prime. This is how the Sieve of Eratosthenes algorithm works. Beginning with the first prime number, 2, the algorithm marks it as prime and marks off every multiple of 2 as not prime. Then it moves to the next number that hasn't been marked off, declares it prime and marks off its multiples. This process repeats until we label all numbers. This method is significantly faster than checking every number individually, but still has limitation when searching for very large prime numbers. For those, we need something better. The Sieve of Atkin is a method that's slightly faster for finding prime numbers. It starts with a list already containing 2, 3 and 5. Then it uses 3 specific formulas: 4x squared plus y squared, 3x squared plus y squared, and 3x squared minus y squared. We begin with both x and y set to 1 and compute these formulas and write them modulo 60. If the result of the first formula is one of those numbers, we add the value to the list of prime numbers. For the second formula, we add the value to the list of primes if it's equal to one of these numbers. And the same for the third expression. This step is repeated for every x and y values up to a limit we choose. There's one more step after this, starting with the first number on our list after 2, 3 and 5, which would be 7, we square it and then remove from our list every multiple of that square. We repeat this process with the next number in the list, and so on. Using the Sieve of Atkin, we can identify prime numbers up to 1 billion in less than a second on modern computers. However, for finding extremely large prime numbers, those with thousands of digits or more, we need even more advanced methods. The Sieve algorithms are great for finding prime numbers starting at the beginning, but they aren't ideal when we just want to know if a specific number is prime without checking every possible divisor. That's where Fermat's little theorem comes in handy. It states that if p is a prime number, then for any integer a smaller than p, a to the power of p minus a is divisible by p. We can write it as a to the power of p is congruent to a modulo p. For instance, to see if 7 is prime, we could use 2 as our a, raise 2 to the power of 7, subtract 2, and see that the result 126 is divisible by 7. So we can conclude that 7 is prime. Well, actually we can't. Take the number 341. Using 2 as a makes it seem prime because 2 to the power of 341 minus 2 is divisible by 341. But 341 actually isn't prime. If we try again with a equal to 3, we find that 341 doesn't pass the test, indicating it's not prime. Doing more tests with different values of a increases our confidence in the result, but it's still not 100% certain due to Carmichael numbers. These numbers trick the theorem for any a we choose, making them seem prime even though they are not. There are relatively few Carmichael numbers, just 43 up to 1 million, but their existence means using Fermat's little theorem only gives us probable primes. We can't be entirely sure we have a prime number, just highly likely. The Miller-Rabin test is another method to check if a number is prime. First, we take a number n that we want to test, and we write it as 2 to the power of x times y plus 1. Let's say that our n is equal to 221. We can write it as 2 to the power of 2 times 55 plus 1. Next, we pick a number a that's smaller than n, let's say 13, and we raise it to the power of y, which in our example is 55. This calculation would usually result in a very large number, but we are interested in the remainder when it's divided by n. We get a result of 208. If it's not 1 or minus 1, we square it and find the remainder once more. 208 squared mod 221 is 169. Now we only check if it's equal to minus 1. 169 is not minus 1, so we squared the second time. In total, we squared x times and check if the remainder is minus 1. After squaring the second time, we get 52 modulo 221. It's not minus 1, so we can conclude that 221 is not a prime number, and we are 100% certain of it. Let's try with different number, for example 37. It is equal to 2 to the power of 2 times 9 plus 1. And let a to be equal to 8. 8 to the power of 9 modulo 37 is equal to 6. We didn't get 1 or minus 1, so we square it. And we get 36, so it's minus 1 modulo 37. So we can conclude that 37 is prime. Probably. There's around 1 in 4 chance that 37 is not actually prime. To be more confident, we can test it with different values of a. If we test it with 11, we get that 11 to the power of 9 modulo 37 is equal to minus 1. Now, there's only 1 in 4 squared chance that 37 is not actually prime. In this case, 11 and 8 are witness numbers, because they say that 37 is prime and we know that it is. Now let's try with n equal to 85 and choose a to be equal to 13. 85 is equal to 2 to the power of 2 times 21 plus 1. So we raise 13 to the power of 21 and modulo 85 it is equal to 13. We square it and we get minus 1 mod 85. We know that 85 is not a prime number, but 13 is saying that it is prime. In this case, 13 is a liar. For every number n, there are on average 25% liars. If we test a number n with at least 5 different randomly chosen a's, and they all say that n is prime, we can be 99.9% sure that n is really prime. The Miller-Rabin test is better than the Fermat test, because there are no numbers that will look like they are prime for all values of a. For any composite number n, there will always be an a that shows it's not prime. The primality tests we talked about are quick, but come with a catch. They can't guarantee a 100% accurate result. For absolute certainty, there is a method called the Agrawal-Kayal-Saxena primality test. This test relies on a special property. If p is a prime number, then when you take x plus 1 to the power of p and subtract x to the power of p and 1, all the coefficients in the resulting expression are divisible by p. Thanks to some clever improvements, the AKS test is the fastest known method for conclusively determining if any number is prime. However, fast is relative. It's still quite slow for very large numbers. For example, testing a number with 1000 digits using the AKS test on a modern computer would still take years. The biggest primes discovered so far are much larger than 1000 digits. So, how were they found and how do we know that they are prime? The prime from the beginning of this video is equal to 2 to the power of 2281 minus 1. The largest prime number we know is also of the form 2 to the power of n minus 1. This is not a coincidence. Prime numbers of this form are called Mersenne Primes. The 6 biggest prime numbers we know are Mersenne Primes. This is because there's an easy way to test whether a number of this form is prime. The first Mersenne Prime is 3, the next 7, then 31, and so on. As you can see, powers of 2 are only prime numbers. There's a simple proof to understand why if n is composite, then 2 to the power of n minus 1 cannot be prime. Let's assume n is a composite number, meaning n can be broken down into two smaller integers, x and y, neither of which are equal to 1 nor n. 2 to the power of xy minus 1 can be written as 2 to the power of x minus 1 times 1 plus 2 to the power of x plus 2 to the power of 2x up to 2 to the power of y minus 1x. So 2 to the power of xy minus 1 is divisible by 2 to the power of x minus 1. So we know that if n is composite, 2 to the power of n minus 1 is also composite. But it doesn't imply if n is prime then 2 to the power of n minus 1 is also prime. A clear example of this is when n is equal to 11. 2 to the power of 11 minus 1 equals 2047, which is not a prime number. Before we look on how to check whether a Mersenne number is prime, let's see what the perfect numbers are, which have a fascinating connection to the Mersenne primes. A perfect number is defined as an integer that is equal to the sum of its divisors excluding itself. Another way to look at it is that the sum of all factors of n equals to n. The smallest perfect number is 6, since its factors add up to 6, and including 6 itself, they add up to 2 times 6. Following 6, the next perfect numbers are 28, 496, and so on. The link between Mersenne primes and perfect numbers is quite straightforward. The nth Mersenne prime, when multiplied by 2 to the power of n minus 1, yields a perfect number. For example, the first Mersenne prime times 2 to the power of 2 minus 1 equals 6, the first perfect number. To understand why this relationship holds true, consider the factors of a perfect number like 28. Its factors are 1, 2, 4, 7, 14, 28. 1, 2, and 4 can be written as powers of 2, and 7, 14, and 28 can be written as the same powers of 2 times 7, which is the corresponding Mersenne prime. To prove that it is always the case that we can create a perfect number from the Mersenne primes, let's think of a general example. In general, 2 to the power of n minus 1 times a Mersenne prime of form 2 to the power of n minus 1 is a perfect number. Let's write out its factors as we did with 28. So 2 to the power of 0 plus 2 to the power of 1 up to 2 to the power of n minus 1, and 2 to the power of n minus 1, which is a Mersenne prime, times the same powers of 2. The sum of powers of 2 is just a geometric sequence, and we can calculate it using this formula. This would be equal to 1 minus 2 to the power of number of elements, which is n, divided by 1 minus 2, so it is just equal to 2 to the power of n minus 1. Now we factor out 2 to the n minus 1. This is the sum of all divisors of our perfect number, so it should be equal to 2 times the perfect number. And it is, because if we multiply the perfect number by 2, we get the same answer. To check if a number of the form 2 to the power of n minus 1 is prime, we can use the Lucas-Lehmer primality test. It works like this. We define a sequence that starts with 4, and the next element is always the previous element squared minus 2. So, the second element is 14, then 194, and so on. To use this sequence for testing primality, we look at the nth minus 1 term in the sequence. If our number divides this term, then it's prime. For example, to test if 2 to the power of 3 minus 1 is prime, we look at the second term in the sequence, which is 14. Since 14 is divisible by 7, we conclude that 7 is prime. Numbers in this sequence can get very big very fast. However, there is a trick to manage this. Before moving on to calculate the next term in the sequence, we can take the remainder when it's divided by our number. This step ensures that the numbers we deal with don't get larger than the number we're testing. For example, if we wanted to check if 2 to the power of 13 is prime, we would have to find the 12th number in the sequence, which is very big. But before calculating the next term of the sequence, we can just take the remainder when dividing by our number. The 12th number in the sequence comes out to be equal to 0, so we know that 8191 is a prime number. To prove why this test works, we will need to know a little bit about group theory. Group theory is a part of mathematics that studies groups, which are collections of elements combined with a particular binary operation. Binary means that operation is performed on two elements. Imagine we have a set of all integers. From this set we can form a group G together with addition. We could use any operation we want. We could even define our own operation, but we will use addition for simplicity. For a set and operation to be considered a group, they need to meet a few criteria. Closure. Combining any two elements using the operation must produce another element within the same group. For integers and addition, this is true since adding any two integers always gives you another integer. Associativity. The order in which operations are performed doesn't matter. For all A, B and C in the group, if we perform an operation on A and B and then perform an operation on the resultant C, it should be the same as if we first performed an operation on B and C and then on the result of that and A. For our group this works because addition is associative. Third, there must be an element in the group that when combined with any other element leaves the other element unchanged. It is called an identity element. In the case of integers with addition, the identity element is 0 because adding 0 to any integer doesn't change that integer. And last, every element in the group must have an inverse, which is another element that when they are combined, the result is the identity element. For integers, the inverse of any number is its negative, because adding a number to its negative gives 0, our identity element. A set with a binary operation that meets all these requirements is called a group. Let's explore another group example. Let's define a group X of integers modulo 10 with addition modulo 10. This means when we add two numbers, we take the remainder of the result when divided by 10. For instance, adding 5 and 6 gives 11, but in modulo 10 it's 1. This is needed to meet the requirement of closure. The entire set of numbers we work with in this group is all the integers from 0 to 9. The order of the group is a term that refers to the number of elements in the group, which in this case is 10. The order of an element within a group is determined by how many times we need to perform an operation with itself to get an identity element. In other words, the smallest integer r so that this is equal to an identity element. In this formula, r doesn't denote exponentiation. It means that we perform the group's operation r times, not multiply. For example, to find the order of the element 4 in the group X, we add it to itself repeatedly until we reach 0. The sequence goes 4, 8, 12, which is 2 mod 10, 6, and 10, which is 0 mod 10. So the order of 4 in the group X is equal to 5. But we can keep going and add more 4s. We can see that if we add 4 to itself 10 times, we also get 0. What we know from this is that if we perform an operation on an element A s times and get an identity element, we know that s is a multiple of the order, like 10 is a multiple of 5, but 5 is also a multiple of 5. Order is the smallest s, so it's 5. An interesting case is the element 3. After adding it, we get 3, 6, 9, 2, 5, 8, 1, 4, 7, and 0. So the order of 3 in this group is 10. One important fact that we will need later is that the order of an element in a group can't be bigger than the order of a group. In the case of 3, its order is equal to the order of a group. And we can see that it can't be bigger because to get to the identity element, we have cycled through every element of our group. To understand how the Lucas-Lehmer primality test for Mersenne Primes works, let's start by defining two numbers. X is 2 plus the square root of 3 and y is 2 minus the square root of 3. When we multiply x and y together, the result is 1. Now we would like to express our sequence for testing prime numbers in the terms of x and y. The nth term of the sequence is equal to the previous term squared minus 2. We can say that nth term of the sequence is just equal to x to the power of 2 to the power of n minus 1 plus y to the same power. This holds true for the first term, n equal to 1. Now we can show that if we square it and subtract 2, we get the next term of the sequence. After squaring, we get x to the power of 2 to the power of n, plus 2 times x times y to the power of 2 to the power of n minus 1, plus y to the power of 2 to the power of n minus 2. X times y is just equal to 1, and 1 raised to any power is still 1. So the result is x to the power of 2 to the power of n, plus y to the power of 2 to the power of n, which aligns with the pattern of the sequence where n increases by 1 for each term. So this proves that the nth term of the sequence can be expressed using x and y like this. We have a number mp of form 2 to the power of p minus 1, which divides the p minus 1 term of the sequence, and we want to prove that because of this, mp is prime. So we assume that mp is not prime. If we reach a contradiction, it will mean that mp is prime. If mp divides s of p minus 1, then we can write that s of p minus 1 is equal to some integer k times mp. We can represent s of p minus 1 using x and y. Now we can move y to the right side of the equation and multiply both sides of the equation by x to the power of 2 to the power of p minus 2. X times y is equal to 1, so we get this. If mp is not prime, we can define q as the smallest factor of mp. mp is equal to some power of 2 minus 1, so we know that it is not divisible by 2, so q has to be bigger than 2, and if q is the smallest factor of mp, q squared can't be bigger than mp, because factors always come in pairs. Now let's define a set, not a group, of integers zq, which contains all integers modulo q. Now let's define a set x that contains all numbers of form a plus b times the square root of 3, where a and b are from the set zq. We can define multiplication in x. If we multiply two elements from the set x, we get this, and after reducing the coefficients mod q, we get an element of set x, ensuring our operation is closed within the set. We know that q is bigger than 2, so it means that x is surely in set x. The size of x is equal to q squared, because there are q possible values for a and q possible values for b, and when you consider all combinations of a and b, you get q squared the different elements. Now we define a group x star, which contains all elements from set x that have an inverse under multiplication. The identity element in multiplication is 1, so the inverse of an element c is just equal to 1 over c. So the only element that doesn't have an inverse is 0, because we can't divide by 0. The order of x star is equal to q squared minus 1, since it contains all the elements of x minus the one element that can't be inverted. We also know that x is an element of x star. If q is a divisor of mp, then mp is congruent to 0 mod q. Following this logic, this equation modulo q will just be equal to that. And if we square both sides, we get that x to the power of 2 to the power of p is equal to 1, which is an identity element in multiplication. So we know that the order of x is a multiple of 2 to the power of p. We also know that 2 to the power of p minus 1 is not a multiple of the order of x, because x raised to the power of 2 to the power of p minus 1 is not equal to 1. So from this we can conclude that order of x is equal to 2 to the power of p. Why? Here is a way to understand this. There is a number d and some powers of 2. If d divides some power of 2, for example 5th power, 32, and doesn't divide the previous power of 2, in this case 4, we know that d is not any of the previous powers of 2 because they all divide 16. And we know that d has to be a power of 2 because it divides 2 to the power of 5. So d can only be equal to 2 to the power of 5. We know that the order of an element of a group can't be bigger than the order of a group, so the order of x has to be smaller or equal to the order of x star, which is equal to q squared minus 1, which is smaller than q squared, and q squared is smaller or equal to mp, which is equal to 2 to the power of p minus 1. 2 to the power of p can't be smaller than 2 to the power of p minus 1. We have reached a contradiction. So our assumption that mp is composite and has a factor of q was wrong. Therefore, mp must be a prime number. The Great Internet Mersenne Prime Search, or GIMPS for short, is a group effort where volunteers use free software to look for Mersenne Primes. It was founded in 1996 by George Waltman. The project has discovered the new largest known prime number 15 times. This includes the most recent record breaker, found by Patrick LaRouche on December 7, 2018. LaRouche made his discovery using an ordinary home computer equipped with an Intel processor from 2014. Even with today's technology, checking a Mersenne number that has millions of digits can take a modern computer from a week to an entire month, or even more. However, thanks to the combined computing power of hundreds of thousands of computers from volunteers around the world, GIMPS can check almost 1,000 numbers for primality every day. The prime numbers we have talked about are incredibly large, but there are numbers out there that are even larger. So large in fact that it's impossible to write them down. They have so many digits that their length exceeds the total number of atoms in the universe. To learn more about them, watch this video next.